most recent work that's done on is electromagnetic signatures and black hole mergers.
So we know that merger of galaxies is an important cosmological process, and most galaxies have black holes in their center. So we can expect that sometimes black hole mergers occur. And there are several stages identified in merging black holes. When first the friction during the core of the galaxy, then due to the dynamical friction within the stars, and then eventually you get to the stage where emission of gravitational radiation is the main driving mechanism. And of course, this is this is an important source for LIGO and LISA. LISA sources. LISA should see merge of supermassive black holes to cosmological distances, and then of course it's very important to determine any electromagnetic contemporaneous signal that would help us to identify the whole galaxy, and so it's very important to find contemporaneous electromagnetic signals, if any. So the latest stages of the merging can be separated into two stages, so to say. When the separation is about larger than 100 Schwarzschild radii, the inner edge of the accretion disk follows the orbit due to the viscous stresses. But then, when the distance between the black holes becomes small enough, the emission of gravitational waves becomes fast enough so that the last 100 Schwarzschild radii, the disk basically stays there because it only slowly, viscously, the inner edge of the disk slowly, viscously advances inward, while the two black holes spiral very fast. So the spiraling occurs in a medium which is very devoid of plasma. And that's one of the main problems with detection and electromagnetic signature, because even if something very important happening in the center, some drastic events, the accretion disk, which we usually observe, is far out. And so the changes of the disk's properties generally is expected to be small. Because the edge of the disk is very far. There are some ideas that, for example, the merging of the black holes may get a kick, and then the product may shoot through the disk. But this is kind of possibilities. So generally, it's very hard to excite fluid motions in a faraway disk, especially by weakly, by the fact that matter weakly couples to perturbation of space-time. On the other hand, we know that accretion disk generates magnetic fields through magnetic rotational instability. So if there is an accretion disk around the orbit of the black holes, this accretion disk would generate magnetic field. And these black holes will be moving inside the disk in the magnetic field generated by the disk. And as I will discuss, the motion of black holes through magnetic field may generate electromagnetic signal, and power with some power. There are two ways, I think, to produce electromagnetic power, electromagnetic signal. One is quite solid, another is more fishy, but still I will explain both. Somewhat strangely, they turn out to be of the same power if you do the estimates. First is, if you have a linear motion of black hole through magnetic field, the black hole will act as a unipolar inductor, in a way somewhat similar to IO, how IO excites radio through X-ray emission in Jupiter magnetosphere. So that was the model by Goldreich and Lindenberg in the 60s. So here is your Jupiter, magnetic field lines of Jupiter. This is Io. Io is a conductor. It's a bad conductor, but still a conductor. When it's moving through the field lines, actually rotation of Jupiter is important. But anyway, if the conductor is moving through field lines, it generates potential drop, and that's how the potential drop across Io, that drives the current, and we see the emission as the current slams, the current carrying charges slam into the Jupiter atmosphere. We see few points of Io, Ganymede, and Europa. Secondly, and the second mechanism is, I'm less confident, but it's an interesting idea still. Orbital motion of black holes generates a rotation of space within the orbit. And that might act as a Faraday disk. In a way somewhat similar to Blanford-Znaick model of jet production by rotating black holes. So the same qualitative idea that rotation of space-time may work very similar to Faraday disk. So, and I will discuss these two models next. So let us first do the Schwarzschild black hole as a unipolar inductor. So just first a note, a physical note. Generally, physical interpretation of mathematical results in general is very non-trivial. And the example would be the concept of a black hole was realized 40 years after the solutions were known. That's an example that it's not trivial. And usually it comes down to the question, who is making measurements and what are the properties of your set of observers. And often, even exact mathematical solutions of correct equations seem to give wrong physical answers. So GR is really special in this case, I think. So in the following, the calculations are mostly done in Schwarzschild coordinates. And generally, this is generally not what a local observer moving with the plasma would see. But it has some relation. So don't take the calculations at the face value. There is this subtlety. What is the different observers measures? And also the notion of a local observer is not well defined on the horizon. And as I will argue, there are some invariant quantities here, and also I did calculations in two coordinate frames, Schwarzschild and Kurzschild, and look similar. So there is some physical meaning to what I'm going to describe. So let us ask first a simple question. Black hole in vacuum in straight magnetic field. And that's the solution. So it's B0, that's the radial component, the alpha is the delay function. So if alpha is 1, it's just Z component. Basically the point is that on the horizon B field becomes radial. That's all good, so this is a simple solution of Maxwell equation in curved space. Next, if we now think of a black hole moving linearly in vacuum through magnetic field, then in the frame of the hole, at large distances, there is constant magnetic field and perpendicular constant electric field. That's all good. And if it's in vacuum, by duality, by electromagnetic duality, electric field will look exactly the same as magnetic field. And here is a picture. The solid lines are magnetic field, the dashed lines are electric field, and as you clearly see, there is non-zero E dot B near the horizon. So that's a very strong statement.
How do I see this clearly?
Well, the dashed lines is the electric field, The solid lines is the magnetic field.
But you also have a non-trivial metric.
Yes, but yeah, that's in Schwarzschild metric. That's E and B calculated in Schwarzschild metric. There is non-zero E dot B.
So the fields are perpendicular at infinity.
The fields are perpendicular at infinity, but close in, they are not perpendicular anymore. That's the strongest statement, and everything else will rely on this statement. So again, what I'm thinking is a black hole moving in vacuum through magnetic field. In the frame of the black hole there is cross magnetic and electric field, but there is a non-zero parallel electric field component. Now let us recall how IO works as a unipolar inductor. So in the frame of the IO, for example, if the IO is moving, say, out of the board, there is magnetic field and electric field, but IO is a good conductor, so it wants to screen all the electric fields inside the conductor. So that generates surface charges. And then these surface charges now generated the dipole electric field, which has component of electric field parallel to the magnetic field. So, and that's how the unipolar, so the unipolar, the potential drop is by these surface charges that are induced by the motion in case of ion. So the parallel electric field is generated by real charges. And pulses work in the same way, except there you have a rotating magnetic field. Rotating magnetic field generates inductive electric field. That inductive electric field has component normal component to the surface. That generates surface charges. Those surface charges generate parallel electric field. That accelerates plasma along the field line, and that's how pulses work. The big difference here that in the case of a Schwarzschild black hole moving in vacuum, parallel electric field is generated in vacuum, meaning there is no additional step, so to say, no real charges. That's a big difference from non-GR analogy. And here is the value of this E dot B. It has some angular dependence. Basically, this beta 0 B0, that's electric field. So beta B0 squared M over R. By the way, if you were to use the membrane paradigm, which treats a black hole as a bad conductor, you would have gotten a wrong dependence. It would be M over R cubed. So, yes. So a strong point, a black hole moving in magnetic field generates E dot B, non-zero E dot B. And then we will more or less follow the logic of pulsars. So in case of ion, to complete the circuit, so you generate potential drop. To complete the circuit, you need to know the resistivities and where the resistivity is in case of ion. Crust, core, food points on the Jupiter. It's much more quite complicated. In relativistic flows, you more or less always know that your impedance of free space will be 4 pi over C. So if you know the potential, you know the current, and you know the power. But of course, this can all be calculated as a check. Different ways of calculating your power. So you expect a potential drop of the order of velocity times size times magnetic field, which may be of the order of 10 to the 14 volts, which is huge. And typically you expect that any stray particle that is accelerated to typically GeV in pulsars will break a vacuum through various electromagnetic processes, usually via emission of a photon, and then inverse quantum scattering and ensuing pair production. As a result, you will try, the secondary plasma will try to kill the parallel electric field. And as a result, you will generate an induced density. And in this case, you can calculate exactly all the density. The typical value, well, it has some complicated angular dependence, but the typical value looks very familiar. It's magnetic field, velocity over Schwarzschild radius over 2 pi c, which of course reminds Goldreich-Julian charge density if we replace velocity over gravitational radius by effective angular velocity. So a same combination pops out in this case. So the angular and radial dependencies are quite complicated and messy. So what I plot here is the contours of constant charge density, positive and negative. Magnetic field is along Z, motion is along X, electric field is along Y. So there's somewhat complicated surfaces of constant charge density. What is interesting, there is generally a surface where the induced charge density is 0. And that's this red line. That's one of the cross sections. I think it's ZX. So induced charge density is 0. And of course that reminds that in case of pulsars, there is also a region, there is also a surface where induced charge density is 0, and that's called outer gap. So here you will have surfaces similar to the pulsar cases. Basically, say here you would expect induced charge positive, here you expect induced charge negative. So there is outer gap where induced charge is 0. For example, here is a density along the field line, along 4 field lines starting at the equatorial points. And as you can see, there is a 0 charge density somewhere on the, as you go along the field line. Next, it turns out that for the even for the smallest velocity, there is a region near the horizon where the first electromagnetic invariant b squared minus e squared changes sign. And that means that within these regions, electric field is larger than magnetic field. And that means that there will be some kind of strong dissipation in those regions. And this is something new. In pulsars, no such regions appear. Then you can calculate the drift velocity, which is of course defined where electric field is smaller than magnetic field. You can calculate it exactly. Unfortunately, I couldn't find a good plotting program to plot the trajectory. Because it's got a complicated three-dimensional motion. The drift velocity. Of course, far out it's just velocity of the black hole minus velocity of the black hole. Near the black hole becomes very complicated. Now, you can calculate a shape of the equipotential surfaces, which would be a reminiscent of the so-called pair formation front in pulsars. So here I calculate basically parallel electric field along magnetic field, given some constant. And the calculation are either done from the horizon on the field lines that do cross the horizon, or from the equator that do not, on the field lines that do not cross the equator. So this can be kind of more or less an estimate of the location of the pair formation front, where the vacuum will be broken down and from where the current flows will be launched. And On the axis, there will be a hole. There will be no current flowing close to the axis. Far out, you will need to go very far to get potential drop, large potential drop. So there will be a region, around the black hole which will stop the jet, the current flow. But that region is not limited to the field lines that cross the horizon. Okay, so here is an overall picture. So these in red, in pink, are the magnetic flux surfaces. And here are some magnetic field lines. These are the regions where one of the electromagnetic invariants changes sign, where we expect with a strong dissipation. And these are kind of conical surfaces where the charge density changes sign. Okay? Now, what's next? Again, just like with pulsars, there are two possibilities. So electrodynamics demands that there be charge density. You can imagine two very distinct possibilities. The one advocated by Michael and Smith is that a constant charge density is building everywhere in the magnetosphere, and that's it. And this is not the main the main line of thinking in pulsar theories, but the problem is that no particle simulations of the magnetosphere were able to produce an outflow. All the particle simulations by Michael Smith and Lyutikov do show formation of this dead magnetosphere. Still, there is a hope that this distribution will be unstable, the electron instability on longer time scale, and eventually you will launch jets. And then, of course, when people do fluid simulations, there's a very nice production of jets current outflows in case of pulsars. So, and we will adapt that demands on charge density, local charge density, will lead to production of current outflows. And here, I remind you that all the field lines are open in some sense. There are no closed field lines. There will be no dead zones. Well, further out, when probably the assumption that the model won't be applicable anymore, you expect some truncation, but qualitatively there are no dead zones. All the field lines will be operating as a current source. So here how the current will look like. It will be kind of quadrupolar flow. So what I draw here is basically a sign of the charge and the direction of the local magnetic field. There is a current flowing in, flowing out, current flowing in, flowing out. The total current is zero, both because up the same and down the same, so it's kind of double zero. But the typical value of the total current integrated over all distances is velocity, mass, magnetic field in natural units. So, next. So you have a potential drop of the order of m squared E squared. So this will be then the estimate of the electromagnetic power generated by a black hole moving with velocity beta in magnetic field B0. M squared B0 squared beta squared. You can also calculate it as the flux of the toroidal field generated by these currents. So you can, this is from potential. You can, and also you can calculate it as the Poynting flux and as a potential drop squared, because again the resistivity is 4 pi over c.
Do you have an asymptotic solution for the electromagnetic field so that you calculate the luminosity exactly?
Yes. Well, it's the current that is flowing in there that generates B phi.
But
And
well,
that's-
you've given an estimate, right? But the asymptotic in vacuum, this is just pure vacuum.
Yes,
I would think the asymptotic
yes, yes,
delta V and E would be calculable,
yes,
and they are.
yes, yes. Now, and then we can use velocity as Keplerian velocity. And then this is our estimate of power of emerging black holes. Gm cubed b squared over r, and c to the fifth.
And that's exact, and there's no coefficient there.
No, there'll be coefficients there, yeah. Now, this power is typically much smaller than the gravitational wave power, basically by the ratio of the magnetic field within the volume of the orbit to the binding energy. So it's typically much smaller than the gravitational wave energy. Now, Carlos has done simulations where we show very, I think they show what I just presented. So this is a charge density in the, I think, equatorial plane for the two black holes that are moving through external magnetic field towards each other. And there are some strange things happening close to the horizon, which I don't understand, but I'm not sure Carlos and his colleagues understand. But they do show clear formation of this jetted outflow with two currents each. So the experiment is very encouraging. Now, as I mentioned, I foresee two mechanisms for the production of the jets. The second is, as you have so the second will be relying on the Blanford-Znaik kind of type phenomenon, which is, I call it the Faraday disk. The idea is the following: you have a magnetic field and you have a disk, and if you're of radius r, and if you rotate disk with some frequency omega, there will be an outflow launched along the magnetic field. Now, in this case, the frequency of the rotation of the disk is not the Keplerian frequency of the black hole. It's the frequency of the rotation of the space inside the orbit. And we can calculate it in a weak field limit, meaning as a first correction to the Newtonian. And here is a frequency as a function of radius for a ring, for a massive rotating ring. And there is the divergence, which is obviously an artifact of the weak field approximation. But as you can see, inside the ring, the frequency of the rotation in space is nearly constant. So our electromagnetic power would be radius of the ring squared, magnetic field squared times c, times omega r over c squared, where omega is the angular velocity of the rotation of space-time, which is this. And then the resulting power turns out to be similar to the one that produced by the Unipolar inductor. And it's a bit strange, and I don't quite understand this. And many of my colleagues, they think that this is the same, but there is a clear Gedanken experiment when one mechanism is turned off and another is turned on. Again, if you have a linear motion of a black hole, the first mechanism will work and the second one no. If you just a rotating massive ring, the second mechanism would work and not the first one. So here is how I imagine the overall picture. Each black hole, as it moves through magnetic field, launches these dual jets due to unipolar induction. Plus, there may be an overall jet launched from within the orbit. Now, yeah, we can redo everything in Kurzschild, and things look similar, except the only one is that the shape of the E dot B, yeah, where E equals B region, looks a bit different. And And that relates to the fact that this cannot be taken as a physically, locally things may be different than somewhat different than I just described. No. Now next, so far magnetic field was only as a parameter. And there are several ways of estimating magnetic field. And basically this is an estimate of different estimates of magnetic field at the edge or at the inner edge of the accretion disk. And one of the problems is that the accretion disk during the merger is far out at 100 Schwarzschild radii. And so the magnetic field is lower because you are far out where the disk is not as dense. And again, there are different typical scalings, Bondi scaling, anytime type, outflow, analytical luminosity, which more or less they all reduce to more kind of the same estimate of about a kilogauss magnetic field. And then you can estimate the total electromagnetic luminosity, which turns out to be fairly small, only 10 to the 38 ergs per second for a black hole of a million solar masses. So the power is very small. The total energy is very large because you spiral in for a long time. So the energy is very large, 43, 44 ergs total. Again, that's for million solar masses, and again, and the dependence is at m squared. So if you're merging black hole on 10 to the 8, that will jump it by 4 orders of magnitude higher. Next, expected electromagnetic emission. Again, we're going back to pulsars. We know that in case of pulsars, the distribution function of plasma consists of primary beam and a secondary plasma. And we know that this distribution generates coherent radio emission. We don't understand how, but there is a fact. And since we expect similar phenomena in the case of a moving black hole, one might expect coherent radio emission that will be beamed more or less perpendicular to the orbit. So we will have to be preferentially located. Second analogy. We know that again in pulsars there is a lot of GeV emission generated at outer gaps. We don't quite understand how it happens, but again there is a fact. Here the curvature in pulses may be important, but actually maybe not, maybe it's all inverse constant. So they'll be very similar to the case of merging black hole. Plus, there are regions where electric field is larger than magnetic field, where you expect dissipation. You can, in principle, expect some thermal emission from those regions, but probably not, because most of it will be swallowed by the black hole. Plus, since this power may be operational for a year or so before the merger, you might expect some kind of plurionic type phenomena before the main merger. I don't know how easy it is, but as you see, the powers and the total energy are fairly small. But you never know, maybe the mass of the black hole will be large and will be lacking.
You know, the artificial input will be easier to affect the longer it lasts.
Yes.
And so, for example, changing the topology of jets to go from 2 black holes to 1 is something that might be visible for a very long time.
The problem is the power is small.
Well, so could you produce observable jets? Yes, it was detectable.
Yeah, so that's the maximal power. You need very high mass to, it's 38, that's crap. That's of those of a crab pulsar. And we don't see anything like crab even in Andromeda.
Wow. Yeah. I mean, there are assumptions here about how much mass there's around, I think.
No, this is the assumption is magnetic field is main unknown, but these estimates, these are more or less upper estimates. So you expect in reality, this is you can consider this as an upper estimate.
No, but what I'm getting at, I guess, is that you can imagine before the merger, well before the merger, at least both black holes are accreting vigorously, right? They both have jets. They have accretion disks. Each has accretion disks extending in close to the black hole, and they have a vigorous jetted outflow. And then after the merger,
yes,
you only have one, but accretion with some delay.
Yes.
And and the point is, though, that although the delay may be, you know, fairly long on the local manifold time, from the point of view of, you know,
yes,
kiloparsec scale
yes,
structures that may not be that long.
yes. So I think what Chris is saying that each black hole, say if it's rotating, it can work as a Blanford-Zanaev process and launch each jet on its own. With the merge, I'm not sure. I know for a fact that merging spinning black holes, the resulting spin will be smaller. So it's not good. Merge is not good for Blanford-Zanaev.
For that luminosity report, using the maximum magnetic field, which is
These are kind of generic. If you there are different estimates of magnetic field, and the estimates are a little bit different by maybe an order or something like it, or an order of magnitude.
right. For that estimate,
For that estimate, I think I'm using electromagnetic scaling, meaning that magnetic field is carried by the Eddington luminosity.
and then
I think that's the largest of the one the
and the luminosity is meant at the Schwarzschild frequency. The R's, the short R's.
yeah, that's at the merger. Well, that's not really the merger. It's R. The number is at the merger moment, and it is smaller for large R. The size of the orbit. Okay, so the next step. Just like with pulsars, you do model of pulsars to within 10% by vacuum, considering vacuum electrodynamics. So the next step is to do a force-free, meaning charges primary charges were accelerated, they produce secondary plasma, that secondary plasma shorted out parallel electric field, and then you need to consider it in a force-free approximation. And one can write expression for the current. Actually, this expression for the current in terms of magnetic and electric fields and delay function is very general. Actually, it works also for a spinning black hole. The problem here is that there is no symmetry. There is no cyclic variable, meaning that there is no symmetry in the model. Everything depends on everything. Everything depends on all three coordinates, on r, theta, and phi. And typically, the main simplification usually in doing it with electromagnetic and MHD outflows is assume some symmetry. For example, axial symmetry. With axial symmetry, you can reduce everything to one linear equation called Grasha-Farnes, non-linear Grasha-Farnes equation, but it's one. One equation describes magnetic field. But since you don't have axial symmetry, here you are left with two equations, what is called Clebsch variables for the representation of the magnetic field. And plus prescribed electric potential as a function of one of them. So there is no simple Grasha-Farnes formulation of this problem, unfortunately. Next, and here I'm getting way beyond my limit of my confidence.
Are you dealing with hypermagnetic fields here?
Sorry?
Are you dealing with hypermagnetic fields?
No, not yet. Here I'm not doing. I'm not sure which fields I'm dealing with. So in standard model of particle physics, the non-zero E dot B plays a very important role. It's called the triangle anomaly. It is responsible for the pi zero decay. Plus, in some models, it is related to the non-conservation of baryon and lepton number.
Well, not ordinary electromagnetic fields, unfortunately. SU2 gauge fields, or before the electric symmetry breaking.
Yes, yes.
The U1 hypermagnetic, electric hypermagnetic fields would do it, yes.
Yes, so, yeah, I don't know. Here I have a very basic, very simple mechanism. Just shoot a black hole through magnetic field that produces the anomaly. And one of the key things about this that this anomaly decays very slowly with radius. So it's a kind of non-local effect. One other cute thing that usually in those models the violation of a baryon number is related to the helicity, which is topological charge, but here helicity is 0, so it's the divergence of a 3 topological current, 3 topological current. I don't know.
So you're following Roger Penrose in considering fossil black holes from pre-Big Bang black holes that survived and interact with primordial magnetic fields before the electric symmetry break.
Yes, yes. But that's it. All I did is and I stopped because I'm getting beyond my comfortable level. But it's a good idea that moving black hole in vacuum in magnetic field generates an anomaly. Yes. So conclusion: magnetic field moving in vacuum through black hole moving in vacuum through magnetic field generates E dot B. In this case, you expect that there will be magnetosphere of a black hole, which will, in some senses, resemble pulsars. There will be non-zero charge density. There will be large-scale electric current flows. There will be outer gaps, very similar to pulsar magnetospheres. In addition, something new, there will be regions where electric field is larger than magnetic field. You will launch kind of bipolar jets, each carrying a current, so 2 currents up and 2 currents down. Power during merger can be estimated as this value. The power is fairly small. It is unlikely to be detected unless the merger is very massive particles. So, thank you. And I just come back, especially for Chris, I will, Chris Matzner, who just logged in, I will show that that's a magnetosphere of a black hole moving through magnetic field. There is magnetic field lines, these regions where charge density is 0, positive here, negative there, regions where electric field is larger than magnetic field, very interesting electrodynamics that reminds of pulsar electrodynamics. Okay.
Is it in plasma?
In vacuum. Well, like in pulsar, you start with vacuum and it will generate plasma. Thank you. Oh, okay.
So questions for Maxim.
So I'm still a little unclear on how the radiative mechanism you have in mind. You're talking about essentially Poynting blocks
Yes.
for your estimates, but are you imagining this is getting converted very close to the neutron star or very far away? Or?
That both. Meaning, just like with pulsars, we see emission from inside the magnetosphere, and that's what I'm talking here.
That's a relatively small factor.
Sorry?
That's a relatively small factor.
That's true, but say if you get a coherent radio, that could be very interesting. If you get a GeV emission, that also could be interesting. GV in case of pulsars reaches tens of % of spin down. And also in GV it will be very intermittent variable signal. The background is small. Plus, and that's what I mean by periodic emission. When a pulsar wind hits the ISM, the pulsar wind nebula is generated, and we see a lot of emission from the pulsar wind nebula. In this case, similar things might happen. Though again,
that's going to be most of the flux, right? So the baryonic.
Again, the GV emission, according to Fermi, may reach percents, and I think it can be even tens or 10, between 10 and 20% of the spin down. So the magnetospheric emission is may be very efficient. But in principle, yes.
Can you go back to where you show your currents again? Where you show for risk? So, well, one thing was confusing is when you show that 3D random, that it was symmetrical. Right?
It's not axisymmetric.
Okay.
It's not as you can see there's the ears, black hole is moving in that direction, and there is this ears, and this surface is not actually symmetric as well.
Okay.
So it's not actually
So,
symmetric.
so it's not.
It's not actually symmetric. Yeah.
Right, okay.
It's not.
Right. So the thing is that if so the current tones themselves are axisymmetric.
No.
No, so that's right. It just looks axisymmetric to me.
It looks, but it's not.
Okay.
Well, okay. So this is the imposed magnetic field.
Yes.
It is actually symmetric,
Okay.
but the currents that are flowing
Right.
are not actually symmetric.
I see.
So the induced currents are not actually symmetric. And say the shape of this rho equals 0 surface is not actually symmetric. And okay. So these are the charge density on the field lines going out of here and going out of here. So they're a little bit different. So that tells you it's not actually symmetric. Yeah, so the system is not symmetric, and that's one of the problems in finding any analytical solution to force-free condition, because it will be very messy flow inside with 3D flow.
And so the second question relates to the fact that you get the violation of E squared minus B squared.
Yes.
So if I'm a freely flowing observer and I cross that region, like what is it that changes? How do I know that? Why is that?
Yes. So if B is larger than E, that means there is a rest frame where there is no electric field.
Right.
And that is the rest frame of the electric drift.
Yes.
If E is larger than B, that means there is a frame where there is only electric field and no magnetic field. If there is only electric field and no magnetic field, there will be strong dissipation. So usually these effects in the violation of E squared minus B squared is taken as an effect of there will be strong dissipation of currents, and that's how pulsar magnetospheres are modeled, because in pulsar magnetosphere there is a generically problem that you run into problem E larger than B. And what people do, the moment the grid E becomes larger than B, they by hand they put it smaller than B. And I think that was done. What was done here too. I think you saw the regions. Anyway, you saw regions of E larger than B, and it was by hand twist down to E smaller than B. And that means it basically means a violation of a fluid approximation. You will never be able to treat these regions as a fluid.
Right, but you didn't treat it as a pure vacuum, right?
Yes. Yeah. So this is more important for the next step.
Right.
So again, like with pulsars, you can get everything right to within 10% by thinking everything is vacuum.
Okay.
But then there is a next step, which you know, what's the plasma structure of the magnetosphere. So here is, I'm doing vacuum, which is setting up the stage for next state, to try to do it in a plasma approximation. And And the statement is that there will be problems here.
Good, tough problem.
Well, numerically you just crank E, make it more than this or something. But then, of course, you need to make sure that nothing depends on your cranking. So with pulsars, as Anatoly Stepkovsky spent a few years playing with his cranking procedure so that his cranking, the killing of electric field doesn't have a global structure.
So that was an thin equatorial current sheet, which.
Yeah, but it's all global structure. It's a thin equatorial sheet, but it's a global structure in the mesosphere. So you cannot say that.
So, are there any more questions from Maxim?
I didn't quite catch the answer to Phil's question. You're free falling into, or you enter this region with U, and D. How did you get that way? From your standpoint, isn't that something you could measure locally in your Lyutikov frame?
Well, with a free-falling observer, that would be the Kerr shield. Here, the calculation in Kerr shield coordinates, which is a free-falling observer into the observer that falls in a free-falling into the Schwarzschild black hole. So, if he is falling along this direction, he will locally measure electric field larger than magnetic field.
Well, what is it from? The question is what is it from? Is it from the induced charges or what?
No, it's just from the motion of black hole through magnetic field. It's a pure vacuum effect. Just the basic motion of Schwarzschild black hole through perpendicular to magnetic field generates these regions. It's pure vacuum effect.
Any more questions?
It's a bit strange to understand.
Is there any more questions from Maxim? Well, if not, we're going to have some